Hi YouTube. So in this video, let's talk about the Schrodinger's equation and let's carefully deconstruct what every element in the Schrodinger's equation talks about the behavior of that particle in real life. So without further ado, let's jump back to the early 1920s, which was arguably the best decade for the endeavors in quantum mechanics. In 1924, de Broglie discovered matter waves, and right after that, the term wave function came into existence. Wave function is any function whose amplitude squared defines the probability of that particle present there, and which can be operated by rotating and scaling it at different values and different angles in order to get some really interesting observables like energy, momentum, position, angular momentum, etc. But let's talk about the Schrodinger's equation in this video. And in 1926, Erwin Schrödinger came up with this unique relation of the energy operator as the Hamiltonian of the wave function, which I will describe later, which we now call as the Schrödinger's equation. So basically, Schrödinger's equation defines the energy of that particle as first order in time and second order in space. If you have seen my previous video on energy operators, which I really recommend you to watch, you will really understand what I'm talking about. Because the energy of the particle can be defined as rate of change of time in first order and rate of change of position in second order, which is the partial differentiation of psi. So let's get to the Schrödinger's equation, and first let's see what we already know. So from the last video, we already know that our wave function psi is in fact a plane wave, which is some constant, which is the amplitude, times e to the power phase, which is I, times kx minus omega t, where x is position, and t is time. And we operated on this wave function by differentiating it, scaling it, and rotating it in order to get some very interesting eigenvalues. So for example, if you still remember, if I do negative I h bar, that is if I rotate it by negative I h bar and scale it by Planck's constant, and if I differentiate or take the rate of change of psi with respect to position, what I get is the momentum operator. So the eigenvalue for this operator is the momentum of that wave function. And since I got the momentum, it's not hard for me to get p squared over 2m term, which is the energy. So we also realized that if we do negative h bar square divided by 2m times the second order rate of change of psi with respect to the position, this gives us the kinetic energy of the psi. This is not the energy operator since it's not the total energy. In fact, it's the kinetic energy of the psi. And we also observed that since t is depending on omega here, we can get the h omega term, which is the total energy, as the time goes by. So time evolution gives us the total energy. And so I h bar times the rate of change of psi with respect to time, this gives us the energy operator of the psi, which is the total energy of the wave function psi. So this is what we already know from the last video. These are a few operators. This is the momentum operator, and this is the energy operator. So now let's see what the Schrödinger equation really tells. I already told you, Schrödinger equation tells us the energy of the particle, first order in time, second order in space. So let's rearrange these equations. So I can simply write something like this. I h bar times the rate of change of psi with respect to time, which is the energy operator, is equal to this energy, that is the kinetic energy. Remember, total energy is the kinetic energy, that is the energy present inside the particle, and plus the potential energy too. Because if we have a particle here, and if we have, let's say, some planet here, in this case we are looking at gravitation. So this huge planet will apply some gravitational potential on this particle. So this thing will be attracted towards this planet. Because of the external conditions, the potential of this particle, which will be at, if the height is h, it will be mgh. Similarly, things happen in quantum mechanics too. So my total energy can be given by negative h bar square over 2m times the rate of change of psi, second order in space, plus the potential term, which depends on the position. And this is nothing but the Schrödinger's equation in the first place. First order in time and second order in space, which defines the energy operation of that wave function psi. But there are many other ways of writing the Schrödinger's equation too. In a more profound way, I can write this as negative h bar square over 2m rate of change of psi, second order, plus the potential of psi is the energy of the psi. This is what we will generally use in order to solve the Schrodinger's equation. Remember, deriving the Schrodinger's equation is not very difficult since you already know the wave function. More difficult thing is solving the Schrodinger's equation for different potentials. And so I can also write this in some other way. Because this thing is called the Hamiltonian of the function, I can write I h bar times the rate of change of psi with respect to time, which is the total energy of the wave function, as equal to, let's write it down as a separate value or a separate operation of negative h bar square over 2m, the second order change in position plus potential times psi. And this part right here is called nothing but the Hamiltonian operator, which gives us the total energy of that wave function. Hamiltonian operator is one of the, I didn't write it correctly again. Okay, h cap, which is the Hamiltonian operator. And the Hamiltonian operator gives us the total energy, that is the kinetic energy plus the potential energy of the wave function, which is the energy operator. So Hamiltonian operator is also an Hermitian operator, which gives us the observable real value of the wave function, since it tells about the energy of the particle. We will look about this later again. But Schrodinger's equation can also be defined in 3 dimensions. So this was my Schrodinger's equation. Now let's define Schrodinger's equation in 3 dimensions. And since this is a linear equation, I can also write this as following. I h bar times the rate of change of psi with time, which is the total energy, is the sum of all the coordinates in 3 dimensions. So negative h bar square over 2m del square psi over del x square plus del square psi over del y square plus del square psi over del z square. So this is also called the Laplacian of a function, plus also, of course, the potential term. Or in other words, I can again simplify this equation more in order to write a more common way of writing Schrodinger's equation in 3 dimensions, which is del psi by del t, total energy equals to del square operation, but let's write h squared over 2m first, negative h bar square over 2m, del square psi plus v of psi. So this is where you will find this Schrodinger's equation written in 3 dimensions in most of the books. And the message of the Schrodinger's equation is still the same. It defines the energy of the particle in 1 dimension, 2 dimensions, or 3 dimensions as first order in time and second order in space. So it really hints us about the time dependency of the particle as the time goes by. So Schrodinger's equation tells a lot of things, and we can actually solve the Schrodinger's equation for a particle that is present in many other scenarios. For example, if I want to consider a particle at an infinite potential well, then I will have a potential of something like this, where these are infinite potential walls and the potential is 0 at this point. I can also define the particle as simple harmonic oscillator, where I will have the potential increasing like this and potential 0 at the position of the rest. And I can define in many other scenarios. But in this video, we are going to talk about one of this scenario, which is the most basic way of solving the Schrodinger's equation, which is called the free particle. Why do we like free particle? It's because the free particle doesn't have any potential and the particle is free to move anywhere. And that's when we solve the Schrodinger's equation with this term equal to 0 and solve the Schrodinger's equation, which just becomes a differential equation, and get its solutions. So let's solve it for a free particle. But first, let's try to visualize what the free particle looks like before solving its Schrödinger equation.
So as our first example, let's look at the free particle. The particle doesn't have any external potential, but also the particle will not sit still because of the Heisenberg's uncertainty principle. If the particle is still, that means we are confining the particle at a definite position, and we cannot do that. And in fact, the particle will have some kinetic energy and thus some momentum. In fact, at definite kinetic energies, you will have two different superpositions of momentum for the particle, a positive momentum and a negative momentum. And in fact, since we know the momentum of the particle because of the known wavelength of the wave function, the position of the particle will be completely unknown. And so as you can see, the particle having two different momentums, the position of the particle is everywhere, and the position cannot be defined at a single place, unless you do a measurement on that wave function which is significant enough to completely destroy or completely disturb that wave function to confine the particle at a single position. And so for a free particle, it's very simple to visualize two different momentums and the particle being present everywhere. So in this scenario, we are also considering that the particle is completely isolated and no one is emitting or ejecting photons on that particle. And that's why this is the case when the particle will have different momentums and different positions. Whenever someone emits a photon or does any type of measurement, the particle will have a different momentum or superposition of many other momentums and somewhat defined energies. We'll talk about this later, but this should be the free particle visualization. Let's talk about the math now.
And since we know that the particle's potential will equal to 0, I can rewrite the Schrodinger's equation as negative h bar square over 2m del square psi over del x square being the total energy of psi. So this is my differential equation, which I can also rewrite as del square psi over del x square equals to 2m minus 2m e over h bar square times psi. But you also know the value of k, where the momentum is h bar k and the momentum is also equal to square root of 2me. So I can write this as k square is equal to square root of 2me over h bar. And if you want to include the potential term for future examples where the potential is present, you will do the similar thing, but the k value, k squared value, will be 2m e minus v goes here, minus v over h bar. And so I can write this as the function of k being del square psi over del x square plus k square psi equal to 0. And this is my most trivial differential equation to solve the Schrodinger's equation. Which we will be using to solve the Schrodinger's equation for different energy eigenstates, like particle in a box, we have quantum harmonic oscillator, or particle in a potential barrier, or anything else. But for a free particle, we have del square psi over del x square plus k square psi equals to 0, where k square psi is independent of the potential. And solutions of any of such second order equations are given by a e to the power ikx plus b e to the power minus ikx. So these are my trivial solutions for the Schrodinger's equation. And if you try to realize, or if you try to observe this solution, you can see that there are two different values of k in the phase. That means that the particle has two different momentums. And the particle is superposition of two different momentums. It's not in this plus or minus momentum state, but it's in both. And when you catch that particle somewhere, you will find that the observable has that same momentum, because you have already disturbed that wave function. So it really tells us about the time evolution of the particle and the momentum of the particle. Although time evolution is very important and it's very profound, I will make a separate video about this later. But there is something called as the unitary time evolution, which talks about the conservation of probability. It tells us that the probability of that function can neither be created nor can be destroyed. And if I have a wave function, the probability can only shift from one position to the other. And it cannot create itself here unless it destroys some of the probability here. And that's how the time evolution occurs in Schrodinger's equation. And in fact, it's very simple. Since the time evolution is linear, you can also trace the time evolution backwards in time in order to get the backwards time evolution in Schrodinger's equation. These are some very important and interesting concepts which we will cover later. But for now, these are my solutions for the Schrodinger's equation for a free particle. I can also write this solution in cosines and sines, as Euler told me, with some different constants as a prime cosine kx plus b prime sine kx, where a prime and b prime are different constants. So it's just going from one solution to the other solution, but both are similar. And in fact, I will be using this solution for my next video, where I'll be defining the particle in an infinite potential box. So I hope you understand what the Schrodinger's equation tells about the particles. Again, for a recap, Schrodinger's equation tells us the energy operation of the particle as first order in time and second order in space, and every particle has to follow that Schrodinger's equation. And the particle cannot sit still also, so the particle will have some kinetic energy. So this was the Schrodinger's equation, and this was my free particle, and this was my solution for the free particle in Schrodinger's equation. I hope you understand the Schrodinger's equation, and if you have any doubts or any steps that you didn't understand, please let me know in the comments and I'll address your question. Thank you very much for watching. Subscribe for more.